Hi y'all, this WSQ is a review of the fundamental theorem of calculus, and the AP test is in love with the FTC. It's probably the single #1 topic that you'll see all over the exam is the fundamental theorem of calculus. So let's make sure we're really strong in this department. So if you guys would jot down these definitions and see if you can fill in these blanks. Okay, these are the two different forms of the fundamental theorem of calculus. This guy says if g of x equals the integral of f of x dx, so it's saying that the antiderivative of f of x is some function called g of x. Okay, then we know that the definite integral along f of x from a to b would equal, so that is the fundamental theorem of calculus, right? That would equal the function, whatever the antiderivative of f is, which is g, at the top value, and then minus g of the bottom value. So g of b minus g of a. Okay. The second form of the fundamental theorem of calculus tells us that if we have a definite integral from a letter, and I should have stated if a is some number, if a is a constant, and your function has been defined like g of t equals the integral from some number to t, and notice that these two things should always match, g of t and the integral is going from a number to t, okay, along some other function, and you're going to see some other letter, x. It's like the dummy variable. This has to be some other letter. Because what the second form of the fundamental theorem of calculus tells us is that if we have this function definite integral defined from a constant to a variable, then when we take the derivative of this antiderivative, we're just going to get back to what we started, f, but with that t plugged in. Okay, so this would just be f of t. Okay. Hopefully that you remember those two forms of the fundamental theorem of calculus. And we are going to take this just one step further, just make sure we're clear that then therefore g double prime of t, right, if we took the derivative of g prime and got g double prime, then f would equal f prime, or the derivative of f would be f prime. Okay. So this is kind of what we're going to be looking at today. The AP test loves to give these free responses that define a function. So I'm looking at example number 1 now. Define a function g of x as an integral from a number to a letter along some function f, and they've given you a graph of f. Okay, so almost every single year for the past 10 years on the AP test there has been a problem like this. Okay, and you're going to be looking at 4 of them in this section, and you can review on your own if you'd like, and look at all of them. But it's definitely a popular topic. Okay, so please stop the video and read the problem all on your own so you can get an idea of what the problem is asking. Okay. But key idea on this problem is that a function g has been defined as an integral from a number to a letter along some other function. Okay, notice again the x's match, right? And then this is some other letter. And this is what we're looking at. We're staring at f. So we want to think of g as what we would call an area accumulator. G is accumulating area along f, and this is saying starting at 0. So if you guys would jot that down somewhere, you want to think of g of x as an area accumulator. And because it says 0, we're going to start at 0. Other problems, whatever that number is, that's where you'll start accumulating area. So if we're going, and we'll be doing this problem, but if we're going from 0 to 1, if we want to know what g of 1 is, that would mean we were starting at 0 and going to 1, and literally seeing how much area is beneath the curve, right, or in between the curve and the x-axis. Okay. So you're going to see that idea a lot. We're going to be thinking about how much area is getting accumulated between that graph and the x-axis. Okay. So you see all this information. It's telling you it consists of 2 line segments, so you don't have to assume that they're line segments. You know that they're actual lines. Okay. And g has been defined like that. So very classic part A. They're asking us, what does g of -1 equal? We want to know, what does g prime of -1 equal? And we also want to know what g double prime of -1 equal. Okay. So this is usually worth 3 points, 1 point for each part, and it's just the final answer that matters. Okay. Now there are no calculator normally on these types of problems, so you do want to make sure that you know the method of how you're going to show your work. But a lot of times it'll just be, if you get the final answer right, you get it. Okay. So let's make sure we're really good at taking this statement, this g of x equaling an integral from a number to a letter along some other function, okay, and just generalizing it for any x, and then we can specifically plug in -1. So if g of x is the area accumulator from 0, g prime of x, right, would be the derivative of this integral. And since we're starting in a number and ending in a letter, the derivative will just be this function with that letter plugged in. Right, so f of x. And let's take it one more step down, that g double prime of x must have equaled. If I'm taking the derivative of this side, I must have taken the derivative of this side. So that must have been f prime of x. Okay. So we're going to be constantly referring back to these statements throughout the whole problem. And on the AP test, if you write this information in section A, they know that you know this, and they'll give you points for that through, part B, part C, and part D. So make sure you write this statement early on in the problem, and you can refer back to all of these statements. Okay, really important. All right, y'all. So maybe let's attack the first one. G of -1 means I am plugging in -1 in here for x. So g of -1. I want to know what is the integral from 0 to -1 along f of t. Okay. So we want to think about how much area gets accumulated from 0 to -1 along this picture. Okay. Well, this should kind of feel funny, y'all, because we're starting at a bigger number and ending at a smaller number. So this is good review that if you have limits that are not in the order from smallest to biggest, you can reverse those limits. So I can say this is equivalent to the integral from -1 to 0 along f of t. As long as I remember that I will get the exact opposite value. So it'll be the opposite of what it would have been if I was from -1 to 0. But I think it is really helpful if you do that, so that you remember if you're going from small to big, you know that your distance from -1 to 0 would be positive movement. And all of these values up here are positives. So the integral from -1 to 0 will be some positive value. And we're looking at the area of this triangle, right? So a base of 1 and a height of 3. And we take 1/2 of that. So that'd be what? 1 times 3 times 1/2. So this part right here would be 3/2. But the real integral is going from the bigger number to the smaller number. So I have to remember that my answer will actually be the opposite of that value. So -3/2 will be our value for g of -1. So it'll be a -3/2. Okay. And again, looking back at the picture, because the integral was defined starting at 0, you're accumulating area starting at 0. So if you actually truly started at 0 and moved to the left, that would be negative movement. Moving up was positive movement, so negative times a positive. That's why we got a negative as our answer. Okay. Now, the next two are usually a little easier. The area accumulator is the one that probably takes the most amount of time. G prime of -1. Let's look over here, y'all. G prime of -1 is just going to equal f of -1. So if we make that statement here, that g prime of -1 will just equal f of -1. So you're truly looking along your f graph and seeing what output you get when you plug in -1. Well, if I plug in -1, here I am, right at 0. So I know the output along f, if I plug in -1, gives me 0. And therefore my derivative at -1 must have also equaled 0. And then the last one here for today is that g double prime of -1 must have equaled f prime of -1. So if we think about that, f prime of -1, it's talking about the rate of change of f at -1, or the slope at -1, right? And they did tell us that they were line segments, so we don't have to assume, we actually know that this line has a constant rate of change, a constant slope, right? So if we look at the rate of change there, looks like if we start down here at -3, we went up 3 to the right 1, up 3 to the right 1, so it looks like that had a slope of 3, right? So that would give us 3. Okay. So if you're thinking about, like, for your notes, you wouldn't have to write this on the AP test, but you want to think about G here, or maybe for your notes you should write it down. So thought of G as an area accumulator. We thought of G prime, which just equaled f, as like the value that was sitting there along f. So look at value at f. And then G double prime equal to f prime, you're looking at the slope of f. Okay. And so important that you guys understand those basics, because now we're going to take all that information and they're going to ask us a bunch of different questions based on that. Okay, but almost always in these types of questions, they will ask you a series of values, and look for those values to show up later on. They almost always ask you values that will be important later on. You're going to use them in your justification. Okay, so don't forget to always try each part of each problem, even if you don't feel like you know how to do it. At least try so you have a value to use so you can use it in the later parts. Okay. All right, letter B. For what values of x in the open interval from -2 to 2 is g increasing? Okay, so let's just talk about general ideas. G is increasing when, and now truly this could be a quickie, y'all. When is G, or whatever is sitting here, whatever is sitting here is increasing when the derivative of whatever is sitting there is positive, right? So G is increasing when G prime is positive. Okay, so let's think about how we connected this already. G prime, remember we made this statement back here, you're going to be constantly referring back to it. G prime equals F. Okay, so G prime is the same as F. So G prime, which equals F, is positive. And so if you can think about this statement, y'all, when is F positive? Well, you're looking at F, right? You have a picture of F, and you want to know when F is above the x-axis. That's when F is positive. So they asked us from -2 to 2, when is G increasing? Well, G will be increasing along -1 to 1. Now you can include the endpoints or not include the endpoints. I believe that the endpoints should not be included. So I would say from along -1 to 1, right, like that, or -1 is less than x, which is less than 1. Let's see, for what values? Yeah. Any of those would work? Okay, that would be worth, I think I have the grading rubric in front of me, I think that's worth 2 points. So 2 points, the interval and the reason. Okay. Somewhere on your paper you have to connect that G prime equaled F. And the whole point there was that because F was positive along that interval. If you look at letter C, for what values of x in the open interval is the graph of G concave down? So this goes back to kind of like chapter 8 definitions. So G is concave down when, just go for general definition, whatever's sitting here will be concave down when the second derivative of whatever's sitting there, so when G double prime is less than 0. Okay, that's just like your general definition. So to connect it back to this problem, G will be concave down when G double prime is less than 0. Well, G double prime, if we look back, remember G double prime was equivalent to F prime. Okay, so if G double prime equals F prime, oops, algebra for a second there. So if G double prime equals F prime, so if we want this to be less than 0, okay, we're essentially looking for when F, so when F prime needs to be less than 0, that would mean that F needs to be decreasing along those intervals. So when F is decreasing, that's when F prime would be less than 0, right? So if we look back at our picture, we imagine that we were increasing, increasing, and then decreasing, decreasing. So I believe that occurred, what, from 0 to 2? And so that would be from 0 to 2. Now you should never include those endpoints for second derivative. They never include those. That was basically the same grading as letter B, one for the interval and one for the reason. Oh, by the way, I'm on the grading rubric. It looks like they accepted this as a solution, or they accepted this, or sorry, as a reason. So you could just state that, and that worked. You didn't have to state when F was decreasing. I really like that answer, though, because that's what you're staring at, and I'd love you to give justification on what you're looking at. So along that interval, G would have been concave down because F was decreasing. Okay. And then letter D, on the axes provided. Now, I did not provide you axes on your notes, sorry. We're going to sketch the graph of G on the closed interval from -2 to 2. So we want to know what G would look like. Okay. So let's pretend that I provided a sketch or axes for you. And this is what it looked like, something along these lines. I had X, Y, and it went out to 2 here, 2 here, 2, and 1, 2. And we want this to be a graph of G. And remember what G was defined as, was the integral from 0 to X along F. So if we think about this, y'all, we so far only know one value, right? Back in letter A, we found g of -1. So if I plugged in -1, back from letter A, I got -3/2. So I know at -1, I should be at -3/2. But that's all I know so far. Okay. So this does require a little bit more work on our part in that we want to get an accurate picture. We do know a few statements though, right? We know from letter B here, we know when g should be increasing. So we know from -1 to 1, the function should be increasing. And that we would probably assume that along the other intervals then, the function was decreasing. Okay, and then part C, we found out when g was concave down. So then we can maybe assume on the other intervals that that's when g was concave up. So we'll use those two pieces of information, plus the points that we can find when we plug in the other integer values into our g of x. So I'm going to go ahead and make a table here. I'm going to plug in -2, I already know -1, 0, 1, and 2, just to give me some dots to put along my graph so I can accurately sketch. Okay. So, oh, and it's super important that we have a sketch here of f of t, because remember we are accumulating area along 0 to our given x value along that f function. Okay. So maybe we can start at the easiest value, which would be 0. Okay, because this guy here, I would be plugging in 0 in up here. So I would be integrating from 0 to 0 along some function. Okay, how much area gets accumulated if you start at 0 and end at 0 along this function? Well, if I'm starting at 0 and ending at 0, no area has gotten accumulated, which is kind of nice. So I'm at 0, 0. So there is another point along G, is that I'd be at 0, 0. And we're graphing G, y'all. What if I go over to 1? So the integral from 0 to 1, right? 0 to 1. So that would be, you know, positive moving to the right. These are all positive values, so this would be some positive. And I didn't say this earlier, but I did notice the symmetry involved in this problem, right? This was the exact same mirror image as this over here. So I know that this will be the exact opposite value as what I got at -1. So I know this will be +3/2. So if I plotted that on my graph at 1, I'm up here at +3/2. If I plug in 2, so if I plug in 2 here, the integral from 0 to 2, so 0 to 2. Remember this was at a peak at 3 and this was at a minimum here at -3. And so if I integrated from 0 all the way to 2, we knew that this was +3/2. And then as I move from 1 to 2, this turns into negative, right, because I'm below the x-axis. And this was the exact same size as this, so this was -3/2. So +3/2 and -3/2 cancel out, and that would just be 0. And then moving backwards to -2, same thing happens. I'm starting here at 0, moving back to -2. Okay. Technically, if I was moving backwards this way, the integral from 0 to -1 would technically be -3/2. And then this down here would be a +3/2, and those two would zero out. So it would be back to 0. Okay, so I didn't plug those two. At 2, I'm at 0, and at -2, I was at 0. And then this is where your concave up and concave down and increasing decreasing behavior will come into play. So letter B, we knew that G was increasing from -1 to 1. And hopefully you can see these dots, like hopefully you know that these will get connected. Okay, so increasing. But let's check the concavity. It said it's going to be concave down from 0 to 2. So I knew the function, at least from right now, from 0 to 1, I knew the function was increasing, but it had to be concave down, so it looks something along these lines. Okay. And then also to the right of 1, the function also had to be concave down, and since the function stopped increasing at 1, I know now that the function must have been decreasing, so it must have gotten connected in that way. Okay. I knew from -1 to 0, the function was increasing, and since in part C, these values didn't come up as being concave down, we can assume that those would be concave up. And we don't have to assume, right? We can look back at our picture. Because f was increasing along that interval, I know that g should be concave up. Because f was negative to the left of -1, I know that g should be decreasing. Okay. And on the grading rubric, it looks like that got you 2 points as well. So knowing that -2, 0, and 2 were all zeros got you a point. And then having the appropriate increasing, decreasing behavior and concavity behavior got you the second point. Okay. All right, y'all, so I'm not going to be able to get to the second example on this whisk. If you want to give it your best shot, that would be great. If not, I'll film another whisk tomorrow. All right, y'all, good luck.